Okay, welcome back for another wonderful week of numerical algebraic geometry. I'm very excited to embark on this section of the course. It's about one of my favorite ideas, which is monodromy. So I expect you to have taken a course in group theory. So if this is not super duper fresh, if this week might be a good week to review some things. I'm happy to go, at whatever pace is necessary to make sure we're all understanding what's going on. Okay. So the story before in the parameter homotopy section was that you have some parametrized polynomial system, capital F. It depends on some variables, x1 through xn. It's got to be square for now. And it also depends on some parameters p1 through pk. And so if you look at the zeros of this, without distinguishing variables from parameters, you get some subvariety of this product of affine spaces, or just product of complex vector spaces. You got the solution space, which I decorate in the subscript by x, because that's what we're thinking of as variables. And then you got the parameter space, which we decorate in the subscript as p. So we got n variables, n equations, k parameters, and k can be whatever you like. So this variety is called the incidence variety. And there's a very natural map down to the parameter space. All it does is it takes a solution parameter pair, x comma p, and it forgets about the solution. So good old-fashioned forgetful projection map. And in terms of functions, this very nicely encodes a lot of the things we want to think about in numerical algebraic geometry. As the geometric picture looks something like this. If we pick some random point in the parameter space or the space, its fiber will be some number of points upstairs, which we think about as the solutions of the polynomial system indexed by those parameters. The parameter continuation theorem tells us that this number of solutions is generically well defined. So that means that outside of a closed subvariety of the base, the number of points in a fiber is always exactly some number t. Okay. Well, the number of regular points in a fiber. Okay. And sometimes it's useful, and it will be useful in this section, to fix a base point, we'll call it little u, and identify the solution set, which we'll call capital omega u, with just the numbers 1 through d. Okay. In other words, we're going to label our solutions. We're going to enumerate them. We're going to write them in a list. We're going to put them on a computer. Any of these things always induces some order here. So I can talk about the third solution, the fourth solution. Now, this ordering is, of course, arbitrary, right? You can pick any one you want, but we are going to fix some order for now. Okay. Questions so far? Okay. So this is all not news, but there's surprising consequences to what we've set up in this course. And it brings about the idea of monodromy, which you can engage with the idea of monodromy in the context of numerical algebraic geometry in any of these 4 ways. These are 4 examples of kind of mantras I think about when I think about monodromy in numerical algebraic geometry. First and foremost, I think I saw it first as a new way to solve polynomial systems. So far, we have been solving all of our polynomial systems by embedding them in some family of polynomial systems, finding a really nice member of that family that we can solve super easily, and then tracking those start solutions to our special polynomial system. Okay. But this is going to give us a fundamentally new way to acquire those solutions. This idea of mod. It also is a way to encode symmetries in your polynomials. So for example, I bet you all could solve the following degree 10 polynomial by hand. X to the 10 plus 17, x to the 5th plus 12. You could all solve this by hand and give me a description of the solutions. Because you would just do a change of variables like this. And you would then solve this quadratic. And then just say, oh yeah, it's the 5th roots of these two solutions. All right, so what's going on with that polynomial system? Well, there's a ton of symmetry happening. And monodromy is going to encode this type of symmetry. Okay. In particular, this polynomial system, in one variable and one equation, has solutions which are expressible in terms of radicals. Why? Because you can express y in terms of radicals using the quadratic formula. And then taking 5th roots is an a-okay thing to do when you are required to express things in radicals. So in Galois theory or field theory, which is not a prerequisite for this course, you hear about being able to solve things in terms of radicals and how this is controlled by some Galois group. And indeed, in the context that we're looking at in this course, solving is controlled by a so-called monodromy group, which actually turns out in and of itself to be a Galois group of some field extension.
Always?
Yes. Okay. And this idea of monodromy is still being developed in the research. So I don't believe it has been fully taken advantage of. So I'll talk a little bit about one of my recent papers where we use this concept of monodromy to reduce memory requirements for storing solutions to polynomial systems. And when I say reducing, I mean going from like gigabytes to kilobytes. Okay.
Wow. That's impressive.
But when I tell you the idea, it's going to be obvious. Okay. And so this is really, really ripe for people to think about and to think, well, what kind of things can I do given these facts that monodromy shows up in the numerical exchange. Okay, so that's my introduction. So there's a bunch of background that I want to talk about in order to talk about this stuff legitimately that do not show up as prerequisites for the course. I'm not completely sure the best order in which to do this, so I'm just going to pick an order and just go ahead and stop me if there's something you would like just a refresher on or anything like that. Okay, so I want to keep this pretty flexible and reroutable as necessary. So let's think about permutations for a second. So if you have a set, then you can pick up another set of bijections. From that set to itself. It's called the symmetric group on that set. Okay. Our set's a 5. So in this class, when we have a finite set, which we will, we will often identify set of bijections on omega with the set of bijections on the first D natural numbers. And if you look in the notes, there's this super fun Gothic German S for symmetric group. I prefer to do that when I'm writing LaTeX, because I like to use S for other things sometimes. Okay. It's called the symmetric group. And its elements are permutations. Specifically of these first three natural numbers. Let's do an example. Let's pick something in S6. How about sigma? Okay. So I haven't told you anything about the notation I'm using, but now I will describe how what I've written is a function from the first 6 numbers to the first 6 numbers. Okay. And I will do that by just writing down where each number goes. I, let's do sigma I. So 1 goes to 3. So what you do is you just look at these sections of numbers delimited by parentheses. And you think of these as cycles. So what does that mean? Well, 1 goes to 3 and 3 goes back to 1. Okay, so these are cyclically listed. Similarly, 2 will go to 6, 6 will go to 5, 5 will go back to 2. Okay. And this is called the cycle notation. Now, the question, if you've never seen this before, is where the heck did 4 go? 4 goes to itself. Writing this would be redundant. Okay. Especially if you're looking at things like 100 elements or something like that. Okay. And I say this is the cycle notation, and you go, whoa, 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 can't I do this, for example? And indeed, yes, you can do this, and everybody would probably know what you mean. And indeed, it is the exact same function that's being represented here. But when I talk about the cycle notation, I mean a particular way of writing something like this. I want the first element in each cycle to form an increasing sequence. And I want the first element in each cycle to be the smallest element in that cycle. So for example, this would not be the cycle notation for the bijection somebody wanted to write down, because the first element listed in this cycle is not the smallest element in that cycle.
Okay, so instead of 3, 2, 1, the cycle 3, 2, 1, I would write, say, 1, 3, 2.
Indeed. If you wanted to claim that it was the cycle notation. Again, everybody's gonna know what you mean. Otherwise, sometimes it's actually useful to relieve yourself of this constraint. For example, writing down inverses of permutations become very easy, especially when you remove yourself of this constraint. Right, because if I wanted to undo 1, 2, 3, inverse in the sense of inverse function, I would just reverse the whole list. Right, I'm switching the arrows. Okay. Okay, so that's a little refresher on what permutations are. Okay. I'm gonna collect some basic facts about permutations. We may or may not use later. The cycle type of sigma in SD is the partition of B given by the cycle lengths. So for example, the cycle type here is 3, 2, 1. It's partition of 6, since 3 plus 2 plus 1 is 6. And indeed, this permutation has a cycle of length 2, a cycle of length 3, and a cycle of length 1. I've just written it in weekly decreasing order. Okay, so the cycle type of 5. This as an element of S11 is I got 2 cycles of size 3, so 3, 3, 2, and then everybody else gets to be a 1 until I get up to 11. So 6, 7, 8, 9, 10. Elements of cycle type 2, 1, 1, 1, 1, 1 are called transpositions. So we're going to deal a lot with permutation groups. So group is a set G equipped with an associative binary operation that there is an identity element and all elements have inverses. And usually you see this written down in a little bit more formulaic way, but go ahead and review your group theory notes. That's a group. Okay. Subsets of groups, which are groups themselves with respect to the same binary operation. Are called subgroups. And we write for a subgroup something like that. That's right. If I ever write G, it's a group. Okay, so if you give me a bunch of elements of the group and you put Langle wrangles around them, then what you mean by that is the smallest subgroup of G, which contains all of those elements. But what you say is the group generated by G1 through Gk. There's of course a theorem behind this definition, which is that smallest makes sense in an unambiguous way. And in order to know that, you need to know that intersections of groups, subgroups are themselves subgroups, and none of these things are particularly involved to show. And you've already shown it in your group theory. Okay. A homomorphism is a function respecting a function of groups respecting the respective group operations. Yeah, so. Some function goes from some d to some h, such that b of g g1 times g2 is phi of g1 times phi of g2, where you should not necessarily think that this operation is the same thing as this operation. This operation happens in G, this operation happens in H. Okay, that's your crash course on group. Any questions? That should be enough for us here. We now switch to topology. None of you need to have in your background, but if you do, great. Is there a topological space X? If you don't know what a topological space X is, that is a-okay. Just think of some vector space with your usual idea of what an open set is. Okay. Topological spaces just generalize notions of open sets. And thus, perhaps surprisingly at first, generalize the notion of continuity. Okay. No. In X. Is a map. It goes from the unit interval, good old fashioned usual sense that we know and love, to the space X. It is a continuous map. These are the maps of topological spaces. Such that gamma of 0 is gamma of, and that's going to be some little x. It's big X, and this is called the base point of the loop. Oh, I've drawn loops. We've talked about loops. more casually than this, here's a proper definition. When I draw this loop, think of me starting at time 0 and ending at time 1, it's a continuous map from time from 0 to 1 to this space here. Yeah. So technically, okay. That's what it is. Okay. Two loops are homotopic if there is a homotopy between them. I do not mean the same homotopy as the homotopy we've been talking about all class. They're not unrelated, but you will learn this better if you consider them unrelated right now. Okay, so what exactly do I mean? I haven't defined it. Okay, so it's something. Okay, I'm gonna write a T here because I said you should think about this map as something depending on time. But then there's going to be a different type of time, which maybe I'll call capital T. And this is going to be going into our space X. Okay. So we have our little t space across our big T space, and this maps into X. And what I want is that if I restrict to capital T being 0, and I look at this, I'm going to get some loop. Let's call it gamma. So let's give these two loops names, gamma and gamma prime. They're homotopic. If there's a homotopy between them, so it's some function, h like this, where restricted to capital T equals 0 gives you the map gamma. And restricted to capital T equals 1, we're going to get the loop gamma prime. And of course, I'm identifying the maps gamma and gamma prime with the geometry of what I'm drawing gamma and gamma prime. Hopefully that's not too bad. And it needs to be continuous. And then we need this to map to the base point. And we need this to map to the base point. So these vertical boundaries of this square mapping to the base point guarantees that every vertical slice is a loop.
Yes.
Right? Okay, so that's a technical definition. Amongst friends, these are loops which can be deformed to one another without leaving your space. Okay, no breaking the loop apart, no trying to pull it through a hole in the space or anything like that. So that's what homotopic loops are. So for example, the space we really care about is the space of regular values in our parameter spaces. Okay, so everything that avoids this exceptional set that we've been discussing for the last section, which we are calling capital script U, which is our parameter space without this exceptional set. Okay, so everything red is in the exceptional set. And so notice that this gamma is not homotopic to this gamma prime. Okay, there is no way I can deform continuously this loop here, which is going around a point outside of my set, to this one. I would have to at some point pull it through that point. Okay. On the other hand, I can consider the identity loop, which just sends every value between 0 and 1 to the same base point. And that is homotopic to gamma prime here. Because I can just shrink gamma prime up, keeping it as a loop and keeping everything continuous. like pulling a thread. I should say such that. Oh, have that. So in the left-hand side picture, gamma is not homotopic to gamma prime, but gamma prime is homotopic to the identity. Okay. And you may guess, as soon as I start using notation like this, that being homotopic is an equivalence relation. And indeed it is. Okay. So we do get equivalence classes of loops that are equivalent to being homotopic. We would write the equivalence class of such a loop with this brackets as usual. I guess everything should be based at some fixed point u. Little x maybe. It's going to be a set that we write as pi1 of big X little x. I think this is the one place in the course where there is no wiggle room on my notation, and it's really unfortunate. Okay, pi sub 1 is very, very standard notation for this set. I would get cast out of YouTube if I called it anything else. Although pi is what I'd like to call the projection map from the incidence variety when we have some parameterized polynomial system down to the parameter space. So the one is doing a lot of work here. It's a totally different thing. This is the fundamental group of X based at X. And again, this definition implies a very strong theorem that this set forms a group. That there's some way to combine equivalence classes of loops up to homotopy and get new loops. Okay. Well, there is. And if you totally skipped your algebraic topology lectures and you were on the exam and you had to like write down what this operation was, you would probably guess the right one. There aren't a lot of choices. So this is some gamma. Okay, so let's think about our topological space, sorry, our space, whatever, as this box that I've drawn, minus all the red points that I draw. We're based at some little x, okay? Great, so if I want to combine that loop and this loop, let's say gamma prime, well, how am I gonna do it? So what do I need? I need a way to take gamma and gamma prime and combine them together to get something that starts at X and ends at X. Okay. And I really encourage you to think about gamma as just some movie, which plays from second 0 to second 1, that motion. And gamma prime is some movie, which plays from second 0 to second 1, that motion. So any ideas?
Yeah, well, you could go half of your time along gamma. And
Yeah,
the
I could do
rest-
this twice as fast.
Yeah.
And then do this twice as fast immediately after, and I would have a loop going from time 0 to 1, which starts at x and ends at x. Okay, so it hits x somewhere in the middle, who cares? It just needed to start and end at x. And it's called concatenation. Okay. Okay, great. And so now you start thinking about, okay, well, why is this thing a group again? All right, associativity is not the funnest thing in the world to show here. Inverses are better, right? So what is the inverse of gamma? Well, what I'm actually going to do is I'm going to go around gamma. I'm going to go backwards around gamma, okay? And you should think about this whole picture as like this stick poking out of this board. And I'm like looping a thread, right? And if I just loop a thread like this, I can't pull it away from the stick, right? And being able to pull will keep me in my homotopy equivalence class. Right. But if I loop it like this and then back, then I've really just drawn something that looks like that. And that as a piece of string, I can just pull around the loop, right? So it is able to move within its homotopy class and just up to the identity loop, which is the one that's just constant. And that, of course, is the identity of the group. Okay, not commutative. So I think I'm ready to state the punchline. I think I've done exactly the background necessary to define very just as before, with some parameterized polynomial system, d to 1 projection down to the parameter space, exactly d to 1 over some open set U, which is just the complement of this exceptional set. I didn't get to this fact before, but if you know it, great. We will be talking about it more, so I will elaborate that if you restrict yourself to the pre-image of that good set of regular values, this is an honest to goodness covering space. Okay. Great. I want to consider this fundamental group. Good. Okay. You should think about this as all the paths starting from U and ending at the parameter U, for which homotopy continuation isn't going to run into any trouble. There's no path crossings, nothing's going to infinity, nothing's landing on a positive dimensional component, because that is the construction of script U. Script U is exactly where homotopy continuation theoretically works right out of the box. No tricks, no end games, no tolerances for infinity required. Okay, cool. So let's take such a element there. Let's take a representative of an element there. If the fundamental group are classes, I want any representative. Again. Okay, so I go around. All the whole time I have d distinct solutions. They're all, simple solutions, nothing singular. Wonderful, wonderful, wonderful. I come back to where I started. Okay. And homotopy continuation then identifies this set with itself, because loops down here become loops up here. Right? Now I might start at solution number 1 and end up at solution number 2, but as a set, I have to end up at the exact same set. Because all the while I have d distinct solutions. Okay. And so what do I get? I get a permutation. But if you'd like, we've identified this already with D, where gamma of solution 1, or sorry, just solution S is D, if and only if homotopy continuation starting at S ends. Right, so if I follow just one of these points, say, call this S, and I just follow one of these along the homotopy given by the loop, I end up at T. Okay, that's the definition of this permutation that gamma gets sent to. Any questions? And indeed, you've already seen this, but when we were doing the Cauchy endgame, do we remember the Cauchy endgame? So we had some bad t = 0 polynomial system, bad in the sense that there was a solution with multiplicity. And so we weren't able to get really close using our numerical methods. And so we had to stop somewhere early, right? But not too early, because we wanted to make sure that as we do a loop around t = 0, the only point in the exceptional set is that point t = 0. In other words, we really wanted to make sure that the loop we were going to write down on the computer represented the element of the fundamental group, which went around t = 0 once. Okay? And as soon as we did that, we could use the Cauchy integral formula, which meant we had to go around. We'd keep on going around until we got back to where we started here. And we had to take the average of the points we collected along the way. Because remember, with like x squared minus t = 0, we would start at like, say x = 1, we would go around and we would find x = -1. So we would have to go around twice, right? And that's because monodromy of that solution 1 around the loop, which is once around t = 0, moves us to -1. So it's a swap. Okay, so we've seen these permutations already. So this is the definition of the map here. It is a well-defined homomorphism. Its image is the monodromy group of pi based at P. Okay.
Could you go over why is it well defined?
No.
I can't picture it.
Yeah, okay, I will include one, a description of why that's the case in the notes. It should follow fairly directly by the definition of U. The definition of U does a ton of work here. It guarantees that this is a covering space. Okay. In fact, this fact is going to follow from this being a covering space. So yeah, I'll dig up a proof. Yeah. Okay, any other questions?
Is this subjective?
No, very much not so. So if you have a branched cover down to an affine line, if you have a parameterized polynomial system, parameterized by one parameter, right, that means you have finitely many points on the affine line, which is the exceptional set. The fundamental group of that is infinite, right? It's tracked just by the order in which you go around each of your points that's missing, right? So it's like free group on number of points missing generators, right? Very, very infinite. Very, very finite. Yeah. Good question.
So then that should not be the injective error, right?
This is an injective math. This is just inclusion.
All right, so
This is the image.
man,
This is not injective, totally. But this is just the inclusion. The next three classes at least are completely dedicated toward getting as much mileage as possible out of the fact that's written on the board here, or kilometrage, depending on where you're taking it from. Okay. And instead of doing a teaser, I think I'd rather leave that for mystery for Thursday. So I'm gonna end the recording. I'll take questions offline.